Okay, the third hour. So right now, I think I finished the method number one. And I'm going to spend one additional hour on the second method called the direct Z-domain design. Each should have the advantage, which is sample time t independent. If you are interested in more detail, please check the panel number 6. Number 6, if you are interested in the detail about the direct Z-domain design. I think from my notes, it contains 2 major steps. The step number 1, I just summarized some design process from panel number 6. So the first one, because right now it's called the direct Z-domain design, so you need to understand how to find a transfer function in Z-domain after D to A and A to D converter. So first requirement, you need to pass the midterm exam. You know the NSD. Only under this background, you can directly design a controller in Z-domain. So first requirement, you need to find the discrete time model. Because at this time, you have to forget anything from the continuous time. We cannot use the continuous time and based on the approximation anymore, because we figure out it is sample time dependent. So first one is, this is our original control block diagram. We are going to design a CZ. The input is the manipulated input for our system, and the output is the manipulated input for the system. Output should be the error comparison signal. This manipulated input, we are going to use the zero order hold, change the digital manipulated input to a continuous time manipulated input. This is a control plane, GS we want to design. Like this, first requirement, we need to know how to develop the discrete time model. We call this as a new system dynamics, SDZ, because we are going to directly design this CZ based on our SDZ property. So we are going to simplify the discrete time model development based on this and the CZ, unit feedback system. By arrow K. Okay, so if you don't know how to check the table, if you forget handle number 1, you have to go back, understand this. Then, second is decide this digital controller CZ based on some closed loop requirement. So, for example, similar to that example, no steady state error, certain bandwidth, stable system, this requirement how to do that. So similarly, I am going to introduce the same whole zero cancellation technology. But the difference is right now, this time, is we do the directly whole zero cancellation in Z domain. If we make sure this is a stable, if this is a stable system, we have the stable NSD 0 and the pole location. We make sure this requirement we can do the pole zero cancellation. For the pole zero cancellation, first, the idea is first we have to derive the CZ beside a CZ. For example, using a PID control, but the idea is decide a CZ0. The location for the controller 0 is the same to the new system dynamics pole location. However, different from method number 1, we directly do the cancellation in Z domain. If we do the cancellation in Z domain, the Z domain pole and the 0 location, we should include the D to A and the A to D sample time effect. So the sample time will no longer affect our control performance. Your pole 0 cancellation should always maintain the same performance independent to the sample time. This is different from the approximation methods because we do the cancellation in Z domain. Okay, so this one is try to eliminate the steady state error. How about the tracing performance? For the tracing performance, right now, we should similar to the continuous time. Decide a controller gain. We can decide a controller gain. For example, is the K value similar to continuous time. The K value to achieve require bandwidth, require closed loop control bandwidth. So I'm going to explain. how to do this. For example, 100. This time I use radio per second. Radio per second. Okay. 100 radio per second. In this case, you don't need to consider the 2 part. although first it's easy for us to understand, but I use radio per second. If I want to achieve 100 radio per second bandwidth, how to do that? How to do that in discrete time? So actually, in continuous time, our closed loop system phi star. I usually use phi and phi star to define the input and the output. So in continuous time, the transfer function is equal to the ratio between the output and the input. So if we decide this as the first order system, like this is our bandwidth from the raw loopers. This pole location define our bandwidth. So for 100 radio per second, I should decide this pole location equal to which value for 100 hertz bandwidth? For 100 radio per second, sorry. For 100 radio per second, I should decide this bandwidth. You can also define BW as K, any control parameter you want. So bandwidth should be equal to 100. So in discrete time, if the relationship between S and Z is equal to exponential ST. So in this case, our bandwidth should be equal to Z is equal to exponential ST. Right now, our bandwidth is equal to 1 minus 100. The pole location is here. So BW is 100, so the pole location is minus 100. So E is equal to exponential minus 100 over T. You can use the bandwidth or control gain to define this. Okay? And the discrete time, the performance is depend on our sample time. So if we assume sample time is 1 second for simplicity, so E is equal to exponential minus 100. I don't have a number because of my notes I use first. What is the value of exponential minus 100? Close to 0, but I need the actual value. Based on the conformal mapping, we have to decide the closed loop location. This is in S domain. Based on the conformal mapping, we change to the Z domain. This disturbed pole location will be equal to exponential minus 100 when T is equal to 1.
3.72乘以10的负44次方。
It will be close to 0. It will be close to 0 for if you increase the bandwidth, it will be very close to 0. Again, depend on your sample time. if you further reduce the sample time, it will slightly move outside the original 0 point. Okay, 100 Hertz. 100 Hertz in continuous time is very simple. We just decide the pole location at minus 100. So 100 radian per second. Next time I will use first. 100 radian per second, the pole is equivalent to minus 100. In discrete time, it depends on our sample time. So 100 radian per second bandwidth in discrete time is equal to minus 100 times t. You still need to know your computer sample time. But S is equal to minus 100. Alright, so we just need to decide our transfer function. For example, this is our final transfer function. In note, we use the GDR, desired transfer function. This is equal to our output, closed loop output and the input. We just need to decide this as Z is equal to this location exponential minus ST. S is equal to our minus bandwidth location. This value depends on your parameter, so I cannot give you this nominator value, but your characteristic equation should be like this. Z minus exponential ST, S is equal to minus VW, like this. Okay? So I'm going to show you the same example, but based on the relative side, not use the linear approximation. Okay, so I still have 30 minutes. I should be able to explain this one. The same example are L row. The same example. L S over R. I have a disturbance here. dt dt. The output is our current. I'm going to use the digital control. 0 order Hall. I can sample the current. CZ is here. This is a CZ. We want to decide the output for this CZ, manipulate input for the IO load. IO load after 0 order Hall. Input is the current error signal, because I'm going to construct a closed loop controller with the current command. Requirement, decide a closed loop control requirement. steady, no steady state error. No steady state error, which means our output and the command sample the output current and our command current should be the same. No steady state error. And the second one, transient performance definition. Transient performance definition, the magnitude based on our frequency response. The magnitude should be close to, I say larger. The magnitude should be larger and almost close to 0.707. This is our bandwidth requirement until 100 Hertz. This means our bandwidth should be equal to 100 Hertz. You need to decide this as a 100 Hertz bandwidth. Third requirement, different from previous example. Sample time is limit. Which means t close to 0. This assumption it doesn't appear. If your customer asks you, you cannot no longer use a high performance microcontroller, or our bandwidth requirement is sufficient high, it's very high. Your sample time is limited. In this case, you need to consider, because the sample time is limited, my customer give me this third requirement. Sample time is limited, and then you need to do the high performance transient performance response. You need to realize, okay, sample time is limited, so the assumption for continuous linear approximation may not be usable. The continuous if you remember the Rohr-Lucas analysis 1 hour ago, actually 30 minutes. It should be 1 hour ago. Right now it's 11:15. I show you an unstable Rohr-Lucas. It's 10:50 or 11. 1 hour ago, if you remember that, okay. If my customer give you this requirement, I cannot use the linear approximation, continuous approximation. So, milestone number 2. I can only use milestone number 2 because right now under this requirement. So follow the step 1 and the step 2. I haven't erased the analysis process. Step number 1. All the analysis process you can check from the handout number 6. I just upload the data from the senior analysis process. Step number 1, you need some requirement found before your midterm exam. Find the NSD. Find the NSDZ. So do you know how to find the new system dynamics? Right now, the new system dynamics, which is the open loop transfer function, is defined by the output current and our manipulated input. Actually, this should be V, because right now this is a physical system. We don't need to set this as N. It is V. So in this case, it is defined by output versus the manipulated input IZ versus the VZ. Last time, this is the final time I derived the open loop NSD equation for you guys. Method number 2. Please, last time to remind you, please remember zero order Hall. The difference between continuous time and discrete time is discrete time has zero order Hall and the A to B sample inference. 1 minus exponential minus ST over S LS plus R. Actually, I have already derived this. One hour ago, so I directly write down the equation for you. This is equal to 1 over R Z minus exponential T over tau. 1 minus T over tau. Tau is the time constant. All right. This is step number 1. SDZ, I find that. I realize right now the Hall location is equal to Z is equal to exponential minus T over tau. Okay, then I can jump to the step number 2. Step number 2 is here. It's very simple, right? Decide the CZ. You are going to apply the pole-zero cancellation. So I just need to make sure the CZ0 is the same to the NSD pole location. So CZ should be equal to Z minus exponential minus T over tau. CZ0. How about the denominator? How about the denominator? And how about the gain? How to do that? Think about method number 1, continuous time approximation. How to do the pole-zero cancellation. Two solution. Right now I only have 10 more minutes, so I show you the same direction from handout number 6. You can check handout later. Next week I show you the other direction, similar to method number 1 based on the PI control, but I show you in handout numbers Number 6. Please remember he introduced a deserved transfer function. The idea is like this. This is our this is the CZ we are going to decide. The CZ we are going to decide. The control plant right now is an SDZ based on the unit feedback system. The overall closed loop transfer function we call this as a deserved transfer function for this one. In this case, I just need to find this deserved closed loop transfer function. This closed loop transfer function should meet these two requirements. No steady state error, bandwidth equal to 100 Hz. Then I can find GZ. I can find a CZ based on this deserved transfer function. I find the G deserved Z first based on these two requirements. As I said, the bandwidth should be located in this point. So I should be able to find this deserved transfer function based on this. It should be located at Z minus, the equation is over there, Z minus its potential minus bandwidth over T. And the denominator is to meet the bandwidth requirement. There should be a K value here to meet the bandwidth requirement. I will show you later, but the first thing is, based on this, I'm going to find a relationship between CZ. Once we know, for example, this is equal to ZT, like this. ZT like this. This may not be the actual deserved transfer function because I needed to calculate the bandwidth later. But for example, I know the deserved transfer function. I can find a suitable CZ based on this GDR because the relationship between these two, G deserved transfer function, closed loop transfer function, is equal to these two, should be the same. So this is equal to based on the Mason's principle. CZ and SDZ. 1 plus CZ. Based on the Mason's principle, it's like this. So an SDZ, I know the NSDZ. Why? Because I passed the meter exam. I know the dynamic model. So an SDZ, I know this. This transfer function, closed-loop transfer function, I'm going to show you later. You should be able to know the suitable closed-loop transfer function. The only unknown variable is CZ. One equation, only one variable unknown. So in this case, the CZ, the relationship between CZ and the GDRZ is equal to, based on the math calculation, this is equal to if GDRZ, we know the GDRZ, or we can decide this GDRZ, CZ should be equal to I still use the hat for this new system dynamics because it contains the parameter we didn't know that. You can edit a head and analysis the parameter sensitivity. If you want to use this method, CZ is equal to inverse NSDZ minus 1 GDR over 1 minus GDR. As usual, for final extent, I think I don't need to give you this equation because this is the same from your middle school knowledge. One equation should be able to solve one equation should be able to solve one unknown parameter. GDR plus GDR C NSD is equal to C NSD. Right? Cross product. And then right now this is the unknown parameter I want to solve. So I move this to left hand side, GDR to right hand side is equal to CZ and SDZ. 1 minus GDR. CZ is equal to SDZ minus 1 GDR 1 minus GDR. How much time I spend to find the GDR? 30 seconds. I think within 1 minute, even for me, my math skill is not good, so for domestic students, sorry, I don't think I needed to give you this equation. You just need to spend you 30 seconds. Just need to spend you 30 seconds. First equation, second equation, third equation. You just need to write a third equation. You should be able to find this. Okay? Alright, I know this. The only thing is GDR. If I can know how to solve this, I can know how to find the GDR. I don't need it. I can directly find the CZ. So the next thing is to find the GDRV. Okay. 1. So let's go back to the analysis process from the handout number 6. if we want to use this dessert transfer function, inverse transfer function to find our controller, the first thing is find GDRZ based on this requirement. So please remember, let's go back to the continuous time. In continuous time, our dessert transfer function for 100 Hz bandwidth, first order low pass filter, we hope we should decide this. Like this is equal to S plus K over K. K is equal to minus bandwidth times 2 pi. This is our dessert transfer function. We want to decide the overall closed loop system as the first order low pass filter. K over S plus K. This in continuous time. How about in discrete time? In discrete time, how to decide a first order low pass filter system, where the filter bandwidth you can select based on the controller gain K value. How to do this? Actually, it's like this. It's modified from the continuous time. We added a zero order hole to our pure integral gain. And we decide a K value here from the signal process. If you have a chance to take the signal process course, this is exactly the same idea to decide a digital first order low pass filter. Phi K phi star K. This is our dessert transfer function. So this is equal to, sorry. New system dynamics for the first order integrator system is equal to Tz minus 1 minus Tz minus 1. So the overall transfer function GDRZ is equal to, this is the open loop transfer function. So it is equal to K Tz minus 1 minus Z minus 1. This is the denominator. This is the denominator. So this is equal to Kz minus 1 minus Z minus 1 plus Kt Z minus 1. For the stability analysis, and And the bandwidth analysis, as I said, I prefer to use the Z format instead of Z minus format. So this is equal to K Z minus 1 plus KT. Okay? Z minus 1 plus KT. This is our G drz. And then the last thing is for the closed loop system, bandwidth is equal to 100 Hertz. Bandwidth is equal to 100 Hertz. So our KT should be equal to exponential minus 100 times 2 pi. Oh, sorry. KT minus 1. This is our bandwidth. KT minus 1 should be equal to exponential 100 times 2 pi times t. It should be equal to KT Z plus exponential minus 100 times 2 pi times t minus 3. And then you can find that KT is equal to which value? Alright. This is the D-star transfer function. And the second process is find CZ. Right now, from this equation, CZ should be equal to minus NSDZ GDR1 minus GDR. It's like this. So NSDZ over here, inverse NSDZ are inverse NSDZ GDR KT Z minus 1 plus KT 1 minus KT Z minus 1 plus KT. Okay, so you do some modification, eventually you will become, assuming ideal parameter estimation, the resulting transfer function is equal to KT. This is our controller gain. And we need a parameter here to eliminate the steady state error. Controller gain, and later for pole-zero cancellation. Z minus 1. So this is the CZ from the directly digital domain design. First, we find the GDRZ. GDRZ with similar to continuous time based on the first order low pass filter in discrete time. We added a zero order hold. And find a suitable bandwidth is equal to this is our GDRZ. KT define the low pass filter bandwidth or our overall system bandwidth. Then CZ is a relationship with NSDZ and our D-star closed-loop transfer function. If we know the NSDZ and know the GDRZ, eventually we can find this closed-loop transfer function. Next week, I will give you more detail about method number 2. And if you have time, read the handout number 6. I will see you next week.